Okay, so everyone submitted the homework. Okay, cool. So the new one now, this programming assignment is coming out, and the request. Oh man, this doesn't work. Oh, it works. And the one which asks you to finish the buffer cast is coming out as well. So just get ready for this, but hopefully tonight. But today, so we're gonna talk about device drivers in Linux. So the idea is the following. Like, huge part of your job will be to reason about performance of device drivers at some point, or performance about IO in general. So we at least need to understand how, like, get some basics about how Linux does it, and then we can talk about how, like, advanced non-Linux solutions can deal with it. But let's start. We'll start slow. All right. So at a high level, like, again, you've probably seen this diagram multiple times, right? So it's you have the operating system kernel here. It's nothing super new. Like, if you took my OS class, you've seen it before. And like, typically kernel constructed as multiple subsystems, right? So, and like, majority of those subsystems, like, besides maybe memory management, thread management, stuff like that, are talking to peripheral interfaces, right? So, for example, network cards, various disks, and even memory, right? And those subsystems are implemented in Linux and in any other operating system as device drivers, right? So not subsystems, but essentially what device drivers are doing, they're somehow try to abstract the low-level details of the hardware interface, essentially, like specific hardware registers which need to be written for the disk IO to start and stuff like that. And just expose a higher level interface to the kernel, something like, okay, read the block from the disk, right? And if you remember in x86, the device drivers, they were very, very minimalistic. In fact, if I ask you a question, so which ones x86 implements? The console, what else? And the console, despite the fact that I call it a console, but there are like two device drivers there. There is a keyboard and a serial line. And although they kind of together, they form a console, right? So this allows you to type something and read from the user input. Serial line was like this. Like, essentially the serial line or the output driver had the two components. So one really went to serial line, and the second one was actually VGA. So actually x86 supports a VGA driver. So if you boot it, it will print something on the screen, maybe on an older piece of hardware, maybe like right now it will not work. But in general, when you were starting x86 in QEMU, right? Remember, you said we were able to see the graphical output as well. And what else? What else? What's the last driver? Maybe two last drivers which it implements. You remember? Which one? Yeah, exactly. So it has a disk or ID driver to read and write the disk. And arguably, depending on how you want to go about it, it also has an interrupt support. And you can also call it a device driver because it's like the specific elements of how to configure interrupts and receive. But that's about, right? So it didn't have many. And in Linux, of course, Linux supports a bunch of them, right? In x86, everything was bundled together, and meaning that it was all compiled in the same kernel. Everything was statically configured, and that's okay, right? So that was a good start. But a specific downside of x86, which is kind of like is different from Linux. In Linux, device drivers, first of all, they are implemented as kernel extensions, right? So they are not strictly speaking have to be. I mean, you can implement it as you can compile them into the kernel, but majority of the device drivers are kernel extensions, meaning that, you know, a third party, if you build a device which you plug on a motherboard, you can write a device driver for this device without really like changing a single line in the kernel in a typical case, right? So that's nice. So hardware vendor they have this capability, and those are actually loadable. And we call them typically kernel modules because they can be loaded dynamically in the kernel. And the second interesting part, which is different from x86, remember, like when we looked at x86, it was using this in and out instructions to some hard-coded addresses like 3F and something like this. I don't remember exactly. And that's fine. But of course, in the modern world, the hardware, the number of devices is so large that they ran out of those addresses and everything is dynamically configured. And it's specifically supported by buses like PCI, right? So let's take a look at it. So that's essentially the goal is to understand today how Linux does it, at least at a high level. Okay, so as I said, device drivers abstract the hardware, right? So in this specific diagram is the idea is that the hardware sits here, on top of it sits the driver, and on top of it sits some kind of a more general kernel layer. In this specific example, it's a virtual file system, right? An application, there are multiple ways how application can access the hardware. And for a while, and x86 is a good example of that, Unix believed that everything can be abstracted as a file. So that's why this one is a file in a dev subsystem, right? So it's just a convention that various hardware devices will show up inside dev. And the application can actually use read and write traditional file methods to access really the hardware. And it worked for a while, it worked okay, right? So essentially you say, look, like serial line is, why not to abstract as something what is called the character device, essentially the device which doesn't have an address space where you write into a specific block, but you just write bytes into it, right? And that's fine, that works nice. So it seems like the file is a nice abstraction, but really, if you, like with modern devices, imagine you have a network interface, which you can also abstract as a file. You say, oh, this is like writing bytes into the network stream, into the network socket, right? And it seemed to be fine, but what happens when you want to write something like configuration parameters? Something like, okay, run at 100 Gbps or something like that. You can say, you can make a design decision, okay, I will still write it into wrap it into the same idea, and I will be writing like a special command. I don't know, C into this character interface, right? And the device driver will monitor the stream and will essentially just at some point understand, okay, this is a command and will do something. Of course, it's a little impractical, right? For multiple reasons. Like a very naive reason is that, you know, what if really the user wants to write this command, right? As not as a command, but writes to one. Maybe this string itself happens to be a part of the I don't know, a manual which is transmitted over the network, right? So then you need to distinguish real commands from plain text. Of course, you can do specific encoding and stuff like that. Sure, we can do it. But it's wasteful. But also, like even monitoring the stream all the time is not a good idea because it's wasteful, especially for high-speed interfaces, right? So this paradigm, and especially imagine like something like the network card and stuff, a network card or like a GPU card. So essentially, they said, okay, look, it worked for a while, but really trying to pretend that everything is a file is not such a great idea. And they kind of started slowly dropping it, right? And today, almost all interfaces support something what is called IO control or IOCTL interface, which allows you to send explicit commands to the hardware, to the device, right? And to the device driver first, and then to the device, right? Okay, and this is where we are in terms of like high-level interface design. But to be honest, even IOCTL like is not generic enough. So modern device drivers can like really something like a high performance disks like NVMe disks. They will allow like some sharing even between the kernel and the user to make sure that user can essentially like user can monitor maybe completion queues of the device without even entering the kernel, and the driver can read from direct. I mean, the driver still can always read from the kernel memory, but essentially support like batches of submitted requests, which is today called something that's called asynchronous IOs. Instead of like even in network interface, instead of sending a single packet, this new asynchronous IO interface allows you to send a batch of packets, because sending one packet is just prohibitive. It just takes too much time, right? So, but at a high level, okay, what I meant to say here is that the way the interface with the device, or between the kernel and device driver, can be different, right? And so don't get really fixated on this. Again, as we move forward with different new flavors of hardware, people will be coming up with more and more efficient interfaces. So that's not probably a point to discuss, and we'll see different interfaces later on as well. But for a while, Linux wanted to stick to this paradigm, which worked well for disks and character devices. So, for example, your disks were showing up in the dev subsystem, and you can really like use application programs like DD in this example to essentially say my input device is a block disk, and my output is some kind of a file, and please like copy it with a step of like 1 megabyte, right? Or do something along those lines. So it was convenient, and the reason it was done this way is that it allowed accessing devices directly from the shell, which is a huge kind of advantage, because you can write a script like that and then immediately do something with your devices, versus if you really need to establish some sophisticated regions of shared memory, this doesn't fly that well. You don't have a interface to essentially type commands in the shell, right? So, but for a while it was fine, but then it suddenly started falling apart. Okay, so cool. So, but what is really happening underneath, right? So, like our machines which we use today, they obviously they provide a CPU, right, which sits over here that might have multiple cores, and CPUs or cores are connected through a memory bus to the memory, right? So DRAM. So DRAM banks are sitting over here, but peripheral devices are connected to the CPU through a collection of buses. And today, the widely used bus is a PCI bus, which is peripheral component interconnect. And typical system, like a desktop or a server system, has two PCI buses, like PCI 0, PCI 1, and they are connected with the bridge. So essentially, you can think of those buses not as about wires, but those are really networks which allow you to send packets between individual destinations, right? And so the packets can probably be reordered, and everything else can happen like similar to a regular network. But the point is that buses allow essentially connect multiple peripheral devices, and sometimes other, like, for example, if this is your USB bus, and USB stands for Universal Serial Bus, right, where you can typically connect a webcam through a web interface, through a USB interface, something like a mouse or a keyboard, then it will be connected to a USB controller. USB controller itself will be connected to a PCI bus, right? So essentially, when a device driver over some USB webcam communicates to the to the device connected to USB bus. So essentially, the packets sent from the device traverse this hierarchy of buses and eventually reach the device, right? And typical thing is that another bus, SCSI, small computer system interface, is again connected to a PCI as a controller. It was a bus designed specifically to maintain hard disk and stuff. And today, network interfaces are typically connected directly to the PCI bus. So just because the PCI is actually the fastest bus, and NVMe interfaces, which are non-volatile flash devices, are also connected to a PCI bus, right? So, okay, cool. So in x86, again, PCI, I think x86 only supported an old ISA bus, right? So, and this ISA bus, it was a relatively simple bus. Let me go back here. And it was working essentially, okay, maybe what we need to talk about is essentially how do we typically talk to peripherals, right? So, and we've seen it in x86, right? So where is my in x86, like the old way of talking to devices was to use this port address space, right? So this instructions like in and out, which you can support up to 64K addresses, and essentially the system kept like memory addresses and device IO addresses in two separate namespaces, right? And then like if you access memory with a move instruction on x86, right? So this you access explicitly with in and out instructions, right? And also when you had this ISA bus, do you remember this, that we mapped, in fact, we loaded in physical memory, we loaded the kernel. Do you remember where, like, when we had our bootloader, where did we load the kernel in physical memory? At which address, do you remember? If it's physical. Anyone? Well, almost in the beginning, but not at address 0, right? Why is that? Exactly, 1 megabyte. Because a region roughly from 640 kilobytes to 1 megabyte was occupied by those magical bus addresses. Essentially, remember, if you write something here, like into the address of a frame buffer, it will show up on your screen, right? Because really, like the hardware was intercepting those memory addresses, memory writes, and doing something with them and sending them to like through those hardware buses to like to the VGA screen, right? So essentially, this was a different specification which was popular back then. I think it was called ISA, right? And what does ISA stand for? Who remembers? Anyone? I don't know myself anymore. And I don't have it in my slides, but doesn't matter. So it's one of the buses, right? And the point is that everything, like all of these devices were assigned to specific hardware. All of these addresses were assigned to specific hardware devices, right? So you can like both in and out address space and memory mapped IO, which essentially an idea that you can write into memory and it will somehow translate it by the combination of a memory and a PCI controller into a signal which traverses the hardware bus and like essentially eventually reaches the piece of hardware. But this configuration was completely static and designed or like decided by the group of hardware manufacturers, right? And the problem which happened with this idea is that eventually they just ran out of those addresses because as the number of hardware devices was growing, the space was essentially exhausted. Plus some devices like, again, powerful both network cards and graphical controllers, they required like larger and larger buffers. Like eventually, if you want to communicate with the hardware device efficiently, you probably need more and more because the latency is growing, the speed is going up. So you really need to make sure that you have a window of outstanding requests which you can send to the device to make sure that you can maintain a specific throughput between the device and the CPU, right? Okay, and so what they decided to do, like essentially a newer buses like this PCI, essentially allow you to enumerate all the addresses dynamically, right? So when the system boots. And the second major idea is that majority of the I/O is not going through the explicit port space, but instead uses something what is called a memory mapped I/O, meaning that the hardware, the CPU and the hardware negotiate for an address anywhere in the address space that can be decided flexibly. And essentially then when the CPU does a memory access, like for example, a write into this address, the PCI and memory controllers translate this write into a PCI transaction, which goes into the PCI bus and eventually reaches the device. And so that allows you to like full flexibility of essentially each device can allocate different like regions of different size. They also can they all are dynamically configured and dynamically discovered when the system boots. And also the third major development is essentially direct memory access. So essentially the bus allows you to send the data between the memory and the device itself without involving the CPU. So essentially the device can copy data directly into a memory region without involving the CPU at all. And at this point, the CPU and you as a hardware designer or as a software designer can have multiple options. You can either wait for the device to send you an interrupt explicitly saying that, okay, look, this DMA access is complete, so now you can take a look at this buffer. Or alternatively, you can use a polling mechanism. And this polling mechanism will essentially just, the CPU itself will be periodically checking some kind of a completion bit in memory, saying that, okay, look, is it completed? And when it's completed, let's say the bit is set. And this allows you to avoid the overheads associated with frequent interrupts. Because if you start thinking about how frequently for example, the network packets are arriving, it roughly takes you, if, for example, to saturate, I think, a 10 gigabit interface with 64 kilobyte packets, each packet should arrive roughly 800 nanoseconds, so roughly 2,000 cycles, right? So every 2,000 cycles, potentially the device can send you. So obviously that's not a good idea because your system will become just consumed by processing interrupts, because even dispatching the interrupt will probably take you longer than 2,000 cycles, right? Okay, so those are the major kind of changes which we haven't seen in XV6. So in XV6, we only saw in and out, or we didn't see memory mapped I/O, if I remember correctly, besides maybe when it was using the VGA driver to write directly into the frame buffer. And this is, remember, our Hello World homework in my class was also like writing directly into the VGA driver. But again, we've never seen PCI before. We only saw ISA. Is it even ISA, Japan? Is it? What is this old? Which bus essentially? Yeah, it's ISA, right? So the one which controls this memory hole from 640 kilobytes to 1 megabyte. I think it's part of the ISA specification. Okay, so and we never seen essentially PCI itself and the ability to enumerate available devices in the system and essentially like build a framework which somehow reasons about it. So that's essentially what we're going to talk about today. But do you like at a high level, do you remember x86 and how it was dealing with device I/O? And what was like from there, I will like essentially will explain what additional things Linux does to make sure that it's like reflects those hardware changes with PCI, DMA, and memory mapped I/O. Okay, the high-level things, a couple of high-level things. So first of all, everything is dynamically configured, no fixed addresses. All devices will show up, and during the system boot will be enumerated by either BIOS or the operating system kernel. All this, all I/O is memory mapped I/O. Essentially, like at some point, the system maps the device, like the memory of the system somehow mapped in such a manner that it goes straight to the device through a PCI transaction. And the third argument, and the third major development is a DMA. So essentially everything is done through direct memory access. So there will be, in x86, we often saw those kind of like loops which said, okay, in some port, and then loop while out of some port, meaning we were waiting for completion of this command, wasting an enormous amount of time. So nothing like that is happening. So essentially what happens is that you will be, I will explain how it works, but you will just send a command to the device saying, okay, something is ready for you, so pick it up, and device will be accessing the memory of the system through DMA. Okay, so what I wanted to talk about, okay, we have the buses, and we will concentrate on the PCI bus, right? So because it's the most widely used today. So memory mapped I/O, I talked about it, so we have it. So essentially, instead of using in and out port space, just make sure that some regions of memory are special and understood by the memory and the PCI controller, and really they are converted into PCI transactions, right? And if you ask yourself, okay, but did I really lose these physical pages, like really? You did. So essentially, because the memory which was under those addresses will never be allocated for anything but just those communication with the devices, right? Okay, at a high level, again, what I wanted to like, I explained that we talk to the devices through a memory mapped I/O, but there is a couple of other things. Essentially, devices operate asynchronously, right? So it takes a disk to read something from a spinning disk. It will take you roughly like tens of millions of cycles, right? And obviously, it's not okay to wait, and you have to structure your system in such a manner that the device can later on send an asynchronous notification to the operating system saying, okay, look, the request is complete. You can now like take a look at it, right? And it's a classical mechanism which is called an interrupt, right? So essentially, or like, for example, you sometimes don't know when the next network packet arrives, right? Will arrive, and so you say, look, you pre-configure the region of memory to make sure that the network card can copy the incoming packet into this memory, and then you, instead of like trying to call for changes in this in arriving packets, you say, look, like send me an explicit interrupt. And polling is the second mechanism. So essentially, modern systems, and this is kind of important, they alternate between polling and interrupts. Because if you're constantly polling, you're wasting your resources on checking what's going on with this memory. And sometimes this, since this memory might be, it sometimes is hosted by the CPU, but sometimes it's actually hosted by the device. And like in order to do this memory read, there will be a transaction to the device and back, and you have to wait for it, right? So typically, modern kernels, they alternate between polling and interrupts. Essentially, you say, look, if I haven't seen any activity in a while, I'll stop polling and I will switch back to the interrupt scheme. And next time something happens, send me an interrupt. And when you receive an interrupt, you say, look, I anticipate the stream of activity, like stream of network packets. So I will keep polling, hoping that I will reduce the cost of incoming interrupts and stuff like that, right? So essentially, the way you communicate at a high level, two ways: either wait for an interrupt from a device, and we saw with the Nexus 6, like keyboard was sending us an interrupt, disk was sending us an interrupt, or poll by reading the designated parts of the memory interface for the changes and incoming requests from the hardware. Okay, cool. Now the question is the following, and this is kind of interesting. So remember I said that if ISA bus, which we saw in Nexus 6, had everything statically mapped in this 64, or not 64, in the region of memory from 640 kilobytes to 1 megabyte. Now I claim that everything can be dynamic. So the system somehow should discover what devices are available, right? Essentially, which PCI slots are populated and stuff like that. So what do you think? What kind of interface is appropriate to do this? Like, you really need some dynamism here. How would you design this hardware interface? So remember, the hardware kind of looks like a tree, right, with branches and buses. And let's just concentrate on a PCI bus. So essentially, but even in this diagram, we see that there are multiple PCI buses, bus number 0, bus number 1. Each bus number 1 has multiple slots, and we somehow have to query whether those slots are populated with some or are sitting empty, and somehow then bootstrap everything from this enumeration mechanism. So how do you think it will work? What would you suggest?
BIOS or some kind of other component with configuration space.
Well, what Jafank is looking for a magic bullet. He says some other component, like maybe BIOS, will give us this configuration space, right? It will somehow, like, imagine you're sitting on a bus, right, with multiple slots. And you say, well, somehow something else will enumerate it for us and will give us maybe some kind of array of available entries in the slots, right? But okay, like, it's a chicken and egg problem, right? So we need to write this piece of firmware, which is BIOS, which needs to do the enumeration. So essentially, hardware designers and software designers have to come up with a protocol which allows this flexible enumeration. What will be this protocol, for example? It just, the reason I'm asking, so we remember a specific idea which is used, which is kind of cutish. It's very simple, but cute. They came up with this idea. There's a couple of ideas here. Remember, okay, maybe it wasn't clear from my exposition, but let me just step back and like redraw a diagram here. So in a steady state, when everything is running, each device is represented with, let's call it a configuration space or bar region. So it's the base address register, right? And it's in your physical memory. But if you write something into it, it actually traverses the PCI bus and reaches a device in a specific slot, right? If you write something here, it will reach some other device connected here, right? Obviously, when we boot, no one knows where these addresses shall be in memory, just because if we do, then, well, you can probably, like, and it's actually done. It's done, I think, more on like system on chips and ARM microcontrollers, and Linux, I guess, supports it when everything is configured statically, and those addresses are known in advance because you say, look, the system is so like static that we know at compile time, we compile a kernel for some kind of a microcontroller. We know that there is like 3 devices connected. We'll give them addresses. That's fine. But in a dynamic case, we somehow have to say, look, like the system starts by saying, okay, I want to take a look at a slope number 0. Is there anything there? And if there is something there, we will then allocate maybe a region of memory and somehow tell this device to say that your address space is located in this physical address. So because device will be able to write these addresses as well, right? And then we'll go and say, look, what about the second slot? Maybe there is nothing, and then you skip it. Then you go like slot number 1. Then you go to slot number 2 and say, look, what is it like? Is it the device? Oh, maybe not. Maybe it's like an entire other bus connected here. And you have to recurse and enumerate what's going on that bus. But this is effectively what this is how it works, and they call it geographical addressing. The reason is the following, right? So, for example, if in a typical system you have this 2 PCI buses, right? So the one is bus 0 is connected directly to a CPU, and the second one is connected to a bridge, right? They can essentially recursively enumerate everything. They give every bus and every device a unique number. So, for example, a bus itself, and there might be up to 256 buses in a system, or when they ran out of them, they introduced the notion of domain. So there will be multiple domains per system, but 256 buses per domain, right? Then inside the bus, each device, or essentially each of these slots, is a device, has a device number. They support 32 per bus. And inside each device, because device might have multiple functions, and roughly speaking, like a video capturing interface can have both a video and an audio capturing function, right? You can have a different function number, right? So it's and they support 8 functions per device, right? But essentially, you've seen it in the past. Essentially, if you do LSPCI, it will list you something like 0, 0, 0, 0, and some numbers and some zeros. And this is like device number, this is the bus number, device number, and a function. And essentially, when you boot, the agreement is that all devices are sitting quiet, but this piece of firmware, which Stefan was referring to, either the BIOS or the operating system kernel itself, can query those buses by essentially using one of those. One port is fixed, like a couple of ports are fixed, and you essentially can issue in and out commands into those ports, saying, okay, please give me access to a device on the bus number 0, slot number 0, function number 0. If there is nothing there in this function number 0, the hardware replies was like not found. And then the operating system knows, or the piece of firmware knows that, okay, there's really nothing attached to it, right? But since the space of those things is finite, you can essentially like recursively descend and query all of them, right? And essentially, and every time you find something attached to a slot, at this point you say, look, I'm not going to do it again. I will not be using this addressing, but instead you will allocate a region of physical memory, and you will instruct the device that, okay, like now this in PCI controller, now this region of memory is allocated for configuration space of a device attached to this slot. Essentially, at this point, they say, look, I queried, I figured out 3 devices attached, and the operating system knows at this point that, okay, some devices, and you don't know yet which ones, right, attached to those slots. That makes sense? And now you say, look, how then okay, now the question is, okay, cool. So we know that some regions of memory correspond to some configuration spaces of some devices attached to the bus. What's next? And imagine we've been through this with like Zapank and I and other students. We were building those device driver frameworks. We just wanted to put, and roughly speaking, in order to submit a paper, we wanted to make sure that we can submit evaluation which reads and writes disk or maybe NVMe and sends and receives packets on a network. So we're not very interested in like developing a broad spectrum of device drivers or anything like that. We just need network, NVMe, and maybe disk, but disk is not critical if we support NVMe, right? So we have this idea that we have a bus. We have this enumeration mechanism. Now we have config spaces. How can we structure the software in such a manner that we can suddenly say, look, somehow we say, look, like there is a device driver, maybe it's implemented as a kernel extension, or maybe it's just compiled into the kernel. But at some point, when a specific, like, I don't know, network interface shows up, which is attached here, we will somehow associate this device driver with this network interface. What can be a clever hardware design to do this? No, MAC addresses, right? Okay, in a way, you're right. So what PCI is doing, they do the following. Let me see if I have any other hours. Not today. They make the following convention. They say that this configuration registers, those things, they are generally device specific, right? And like the minimal number is, I think, 256 bytes, but the first 64 bytes are regulated by the bus standard. And they say that like in the beginning, there will be like several fields which identify the vendor ID. And if you want to participate in this PCI market, you need a central registration with the PCI consortium, I guess. And you will be given a vendor ID, and then you can use it, and it's yours. Device ID is one of the devices which you essentially manufacture, right? And stuff like that. And so at this point, it's kind of like the MAC addresses which you mentioned. In the head of this memory region, configuration space, there will be like something like a device ID and a vendor ID. Right? Now it serves as a unique identifier of a device. Right? Now we know. So whatever we found on the PCI bus, that slot number 0, has this vendor ID and this device ID, right? What do we do next as software developers? No, let's say someone wrote us like, in our case, it was just maybe 3 device drivers, but someone wrote us 10 device drivers. How do we associate between the existing device drivers in the system and existing hardware, which was enumerated as part of this enumeration protocol? Yeah, some lookup tables, Avan says. Okay, cool. So it kind of makes sense to say, look, and we can come up with different ideas here, but when the system was booting, for example, we somehow collected in some kind of a lookup table, we somehow collected information about all available device drivers, right? Maybe we just ask them, okay, what kind of device you support, right? And maybe as part of this query, they say, look, I support a specific device ID for a specific vendor ID, right? Each of them will report this number. And Linux does it slightly different way. And I'll explain it in a second, but just for the sake of it. And then if you have this lookup table, you can say, look, okay, naturally, since we're dealing with PCI, maybe we need a PCI driver itself. So there will be a piece of software which you develop, which will say, I understand how to do enumeration on the PCI bus. And every time I discover a new device on the bus, and like allocate a memory for this memory map IO, I will read the device and a vendor ID, and I will check in this table to see if I can support it, right? And that's essentially, you see when you the system boots, you see this message, and it says, okay, look, I found this device on a bus, and I will find the driver in my lookup table, right? I agree, that kind of makes sense. And then you say, look, at this point, I will somehow start playing with you, and I will say something like, okay, maybe I will ask you more carefully, do you support this like whatever. I thought that there was another, like, there's additional field like subsystem vendor ID, subsystem device ID. So you send a little bit more information saying, do you really support this device, right? And this thing can, like, from there on, it can register with a kernel. And if it's a disk device, it might be registering with an array of available disk devices in the system, right? Stuff like that. Does it make sense? So the reason, the high level point, which I'm trying to explain, I was trying to explain this dynamism, meaning that you don't really know what kind of hardware you have in the system. And every time you boot, it can change. And also if you support hot plug events, right, it can change while you're running. And essentially, you know, you can maybe plug a new device and maybe the hardware raises some kind of an interrupt and your PCI driver says, okay, I mean, I found something new. I don't think you need to rescan the entire bus. Maybe you already know what exists and what is new. But then you do this, you play this game. You say, look, I know that I might have a driver for this, but and then I will query it. So there's one interesting detail about how Linux does it. So it's kind of cute. So again, remember the kernel itself has obviously roughly 9,000 device drivers in a kernel tree. It's a lot, right? So you have a choice. Remember, I said that Linux implements device drivers as loadable kernel modules. Okay, you have a choice. And it's a kind of a sound design choice. You either compile them on all into the kernel as a single blob statically, load it in memory, and then just play this protocol, right? Alternatively, you say, look, I just leave them on disk, right? They will be compiled as some kind of a shared object, kind of like a loadable, it's called a loadable kernel object, right? But roughly speaking, it's just a shared object, similar to how you implement libraries, right? You leave them on disk without loading them into the kernel. However, oops, on disk, you will have a file which contains association between every vendor ID and a specific module which might support it, right? And essentially, the point is, the Linux does it in the following manner. So they provide you with a specific macro here. The macro generates a specific symbol. It's roughly speaking a data structure which says I support a specific vendor ID and a specific device ID. During the compilation process, a tool reads those symbols from all kernel modules. Essentially, it looks for a specific symbol and collects it in a specific file. So essentially, everything is kind of like independent. So all of these things are built independently, right? However, information about them is collected in a file, and then they have this infrastructure which allows them to call out into the user levels. Essentially, when you discover a new thing on a PCI bus, they call into the user level tool, which reads this table. And at this point, it inserts a specific module back into the kernel with an insmod mechanism. Meaning that upfront, they don't load anything. And so during the boot time, or when there is a hot plug event, they essentially say, okay, well, we'll call out to the user level daemon, which is running there. This daemon will understand like, what is it we compiled upfront, and it sits somewhere in a file system. We'll read a specific kernel module, which is tabled, and we'll load it back into the kernel. And upon load, that this thing will register itself with the PCI bus if it's a PCI device. It says, okay, I'm available, and we'll start playing this game of essentially connecting to the device. So it's kind of cute as well that they did it, right? Do you know, Jahang, do you remember the names of specific this device list? And no, okay, I'll come back with this. But okay, but at high level, we got the point. So this is how it works, this querying, right? Any questions about it? All good? Okay, so what's important here is that like every device follows this specification, vendor ID, device ID, like the PCI bus driver enumerates the bus, or maybe it's already enumerated by the BIOS and it just reads this enumeration. And it looks at this vendor and device ID, picks up the driver, starts running, right? Okay, cool. Now the question, like, back to this kernel model. So how does the kernel implement those kernel models? And again, it's not kind of set in stone. Like if you follow this diagram, you say, look, if I only have 3 devices, maybe I can compile everything statically and somehow have a list, static list, and everything will be flying okay. But probably it's not generic. In the long run, even for those toy projects like kind of research or hobbyist style operating systems, you need something more dynamic and more generic, right? Okay, so Linux came up with this idea, and it's not just Linux, but the majority of the kernel came up with this idea of supporting supporting kernel extensions, right? At a high level, as I'm saying, it's an L file. It's compiled as an L file, which follows specific rules, right? And the rules are the following. It always starts and the execution with something what is called an init function, right? So remember I said that this int mode, like, does anyone ever load a kernel module in the kernel? Int mode? No? On Linux, okay. So, and you, like, when you boot Linux, everything just happens like and handled by those daemons, you never maybe even like care about it. But if you ever have to write your own, you probably say, like, you don't want to deal with integration, or sometimes you don't even talk to this PCI subsystem or anything like that, but you really just want to insert the extension into the kernel. And so this, the insertion starts with a specific, the user tool is called insert module, insmod, but there's a syscall, and inside the syscall, what happens is that you kind of pass it. It's kind of like an exec system call, but simpler, right? So you pass to a kernel extension, which is essentially an L file. And this thing essentially says, okay, cool, like I will like relocate it because it's remember, I don't remember if you remember, but in the memory map, which we looked at some point, remember like the kernel shift, when the kernel maps all the physical addresses with a shift, right? Above this area, there will be a region of memory dedicated to those kernel extensions. And this is where these kernel modules are loaded into this region of kernel memory. So essentially, of course, the memory may or may not be available, so you need to make sure that you relocate the addresses for it to run, right? So it does the relocation. So essentially, it loads it in here, in this kernel object area in a kernel. It relocates, it finds a symbol, which roughly speaking is called init, right? And it just calls into that init symbol. And it like follows a specific binary convention, right? And this is a chance for the device driver or any other kernel extension to register with the kernel. Because as you can imagine, the kernel itself, be it, for example, a file system, doesn't know anything about the fact that this kernel module will be loaded later on, right? What instead is happening is typically this extension will somehow register with the kernel, saying, okay, maybe I'm a character device, and then it is added in a specific table of character devices. Or maybe I'm a block device, and then there are different interfaces. You say register character device, register block device, or register a PCI device. And it all, at this point, you register with, let's say, if you're registering like a PCI device, then you register with the PCI subsystem, and it means that the PCI subsystem will find a new kind of vendor device ID. It will ask you, okay, are you the one who supports it? And then you start playing from there, right? So everything starts from this init function. From inside the, like, when you compile against the kernel, you can, roughly speaking, any public symbol you can link against. So you're free to call the entire kernel. right? Any function in the kernel, like memcpy, memory alloc, anything, right? However, since the kernel doesn't know anything about your functions, it will never call anything from whatever. You implement some foobar. How do you advertise this foobar to the kernel? What can be a solution?
Like event structure, I guess, and like there's like different like set of like symbols.
You can choose different implementation paths, right? But following kind of the object convention or object-oriented programming, it's kind of nice that when you register with the kernel, you can provide a pointer to a specific interface. And in C, an interface is a collection of function pointers, roughly speaking. And if you're registering with a PCI device, PCI subsystem, this interface will have PCI-related function calls. Like, for example, one of them is probe. And probe means that I will check whether you support this device. So every time the PCI later on tries to match the device driver with a specific device, it will call a probe and say, okay, do you really support it? And because the kernel itself will never you can implement an infrastructure which allows you to look up all the symbols because you control the loading, right? So since you control the loading, you know all the symbols, you technically can call them. And there are mechanisms to do that. And some, you will see in third-party device drivers when you depend on another device driver or some other kernel extension, instead of calling this function directly because you don't know where it will be in the everspace, you look up the symbol and then you typecast to a function pointer and call it, right? But it's less elegant. And in most cases, you just can get away with this registration of an interface, right? So let me show you an example of a very simple kernel extension, which is this hello module, hello world module, right? So here's it registers these two symbols saying that the module init and the module exit. The module init is invoked by the kernel on the ins mode. It's a user level program which ins mode executes a syscall. It's the same user level thread within the context of the same syscall, which calls this into this init function after all the symbols were resolved and stuff like that, right? And if you say, look, this one doesn't do anything, it just says, okay, I will print hello world on registration. The kernel will maintain metadata about loaded kernel modules, they have this infrastructure of K objects and stuff like that. I don't even remember myself that much, but it doesn't really matter. You can imagine that the kernel knows what it loaded, right? And at some point, if you say m mode, remove a module, then it will just call this exit function, right? And you will have something like print bye-bye, right? And imagine you were executing, if it's a character device, then the interface you're going to be registering with the kernel, right? And you pretend to be a file, you will register a collection of file operations, kind of like seek, read, write, stuff like that. This IOCTL, remember I said that there is an alternative interface which can send any commands, mmap, open, stuff like that, right? And okay, cool. So this is how the interfaces look like. And in your module, you really, for each of those functions, you will, when you create this data structure, you provide a concrete implementation, meaning that you assign a concrete function pointer to each entry, right? And it's kind of clever because it says, okay, it's almost like a higher level programming language. You say the interface is fixed, but the actual implementation is not fixed, and it's nice. So, except that for different classes of devices, the interfaces will be different. So, for example, you can say, look, my read operation, when you register with this specific simple driver of FOPS, right? So that's, you say, look, you don't even have to initialize all the interface functions. You say, I don't support them all. I just support this one, right? And that's what you will pass into the kernel. And your registration will look something like This is the function, right, which you call from the kernel. So like register, what is it? The char def, and character devices, they have a specific convention of like major and minor numbers. You remember it from x6. It's a game. It just, roughly speaking, the operating system maintains, again, reasons are partially historical. So I'm not saying that it's an ideal way to go about it, but it maintains a table of major numbers and minor numbers, and you register it into this table and saying I will be servicing this specific pair of major and minor, right? And so when you pass this registration function, you essentially say, okay, here's my pointer to my interface, which implements my simple driver FOPS, right? And then, like, typically what will happen in a modern kernel, it will, like, under def, it will show up as some kind of like SD A0 or something like that, right? And then the user can say, okay, I want to read it. And when it reads, it goes through the layers of the kernel, but eventually it's your simple read function, right? In a full featured device, it will do something more meaningful, but you got the idea, right? Okay, so that's kind of, okay, clever. So we got the point that, okay, the kernel itself is fully dynamic. So it's like essentially everything is structured around those kernel extensions, and the kernel extension is loaded into the kernel. The protocol which it follows is that it has to register with the kernel. If it doesn't register like my hello module, then the kernel will never call it again because there is no real way to establish this connection and pull back into the device driver, right? This is clear? Good? Makes sense? So, okay, cool. And okay, so this is all kind of like setting up the stage, but now really, let's take a look at least one device driver which implements a high throughput interface to the hardware. And NVMe is one of those devices because NVMe is blazingly fast, right? So NVMe is essentially a flash non-volatile storage attached. Instead of being attached to like a regular SATA or SCSI bus where the typical disks sit, it's attached directly on a PCI. And the reason for that is that because SATA and SCSI buses are relatively slow, and PCI just moves up every 5-10 years, they come up with a new specification. So it's kind of a parcel bus to the buses which exists maybe besides the memory controller bus and the quick bus interconnect, so cross socket link. Okay, cool. So what do you think are the challenges in implementing this fast communication with hardware? What will be hard? We got the stage running, so we know how devices are enumerated by the PCI subsystem. We know how they're loaded in the kernel. We know how they're matched. But now the most important part is like really the user has to do something like a read, and it says, okay, it's a pointer to a buffer where it wants to read something, right? It goes through the kernel at some point, reaches NVMe device driver, and we're sitting here on a PCI bus, right? That's our PCI bus. We have some configuration space mapped, right? But how do we send commands to the NVMe device? What will be the interface, and what will be the performance bottlenecks associated with this interface? How would you build it to make it fast? I'll give you, just to get it running, I'll give you one hint. Remember this story about DMA. Oh, you have a buffer, right? That's where you want to read. You say, look, what if we, in this device specific part of the configuration space, we'll be just writing a pointer to this buffer. And okay, why not to write a size as well, right? And well, we write it here. I told you that it reaches the device. By the way, device will run some kind of an operating system itself, depending on the complexity. But you know, modern devices run like full-featured ARM cores. It's hard to get. Really, no one tells you what they're running. Like, you know, everyone is very, very secretive. But in theory, you can run your own operating system here. You can run some kind of handcrafted, you know, C code. But as the complexity is going up and you support more and more functionality, you can imagine that this one is becoming like a more and more, you know, like full-featured operating system here. But somehow it also receives an interrupt and maybe some low-level hardware parts. You know that, okay, the guy wants, they changed our configuration space, so it means that the pointer changed. And at this point, you say, look, okay, cool, we're gonna do a DMA directly to this thing, right? And we have a couple of options. Maybe we will designate another bit here as a completion bit, and the assumption is that this guy will be polling, waiting for this completion bit, as I was saying, right? Or maybe we're gonna trigger an interrupt, and an interrupt will, you know, preempt execution of whatever it's running, and the interrupt handler will kick in and like process the completion of it, right? That makes sense? It's kind of like, it's not the worst, to be honest. You can do it this way, right? In fact, it's very similar to how x86 was accessing the disk, right? This kind of a protocol. It's just instead of this memory mapped region, they were using ports in and out port space, right? But what is not ideal in this setup? Can we improve? Okay, what's the bottleneck? Let's put it this way. You need what? Well, those PCI buses, as a hardware person, you asking me in directional. To me, it looks like a network. You send packets, I don't care about it, somehow it works. No, the bus is really fast. By the way, I never mentioned the constant. So a round trip on this bus and back is roughly 1 microsecond. It's not super fast, so roughly 2000 cycles, right? But not super slow either. So the buses are relatively fast. And that's why, like, the records, the one, like, if you connect 2 machines back to back with the network cards, I think it's less than a microsecond, maybe 0.7. But they're like additional, maybe like additional assumptions involved for one-way communication, right? So roughly 1 microsecond, just remember this number. So it's not super fast, but it's not super slow either. But then what will be slow? So supposedly, if you write a pointer here, it reaches this device within 1 microsecond, then what? If it's flash already, who can quote me how long it takes to reach something from flash? You probably know, no? I think it's like in the order of like 10 microseconds, right? So 20,000 cycles, right? To send a network packet through a network card, as I was saying, it will take you nanoseconds. Literally, they are so fast. Like sending a network packet, it's just like a bunch of silicon which does this analog or digital to analog conversion, sends within nanoseconds. That's why top of the rack network switches have delays of like 200 nanoseconds. Network cards are about this. So, okay, so this seems like a little bit of a bottleneck, right? Meaning that in the best case, your round trip for this read is roughly, let's say the path through the kernel takes you like roughly 2000 cycles. That's a realistic number, I didn't make it up. The path through the bus will take you another 2000 cycles, and 20,000 cycles to go internally on this device, maybe it's from Intel, very well optimized, will take you 20,000 cycles. So roughly speaking, total process like is what? 20 plus 4, right? Roughly 24,000 cycles, right? Is it fast or is it slow? Or yeah, good, slow is a good answer. Like it's always, you can always do better. How? Imagine you're writing databases or something. Intuitively, you say, look, I never read just one little buffer because you're reading like a giant table. and it may be like a couple of terabytes, maybe smaller, maybe a couple of gigabytes, but still, meaning that you have like, it seems intuitively that you can't do much with the latency because I gave you the latencies, which are more or less minimal, but you can optimize for throughput. You say, look, if I'm reading a terabyte, then maybe instead of sending one packet to the device, I will send a batch, like maybe 32 packets, 32 read requests, right? Even if everything takes the same 24,000, if I divide this by 32, I will get the number of cycles per request, right? But my throughput is going up, which is better, right? Agree with this? So those devices are throughput, those interfaces, sorry, are throughput oriented because latency is kind of, I mean, people do optimize for latency, especially if you go for those, talk to those people who do high frequency trading, they care about latency, right? We care about latency because it also impacts like perceived tail latency and user perceived time and everything. But roughly speaking, we always have to think about throughput. And another wonderful observation here in the modern world, that those latencies will not go away magically anytime soon, because many of those, like those microseconds, they are pushing physical limits. So literally, just like it's propagation of a signal across the wire, or like in case of a flash, it's how long it takes you like this, whatever. I don't really know how flashes, whatever the physics of the flash is, that's how long it takes you like to read it, right? So you have to come up with software tricks to make sure that you program for throughput, right? Okay, we get the problems. Okay, so then instead of this simple naive interface, where we just write one pointer, we want to write a batch or multiple batches or something like that. So how will this interface look like? How can we design it to make sure that we can pipe a bunch of those things asynchronously through this interface? Any ideas? Have you ever seen anything like that in your life? Not yet? What would be suggestion? We saw something like that. Maybe not, because everything what we dealt with was not like a very carefully optimized. So, okay. So many modern devices came up with the concept of those device queues, and they're kind of like ring buffers. I'll show you a picture here. They're very, very simple, to be honest. Like there is nothing really to kind of like, in memory, it's just an array of entries, right? Do I have my pointer? No, really? This guy died. Okay. Right? So it's starts from entry 0 and then like goes to some max. You have some number of entries in a queue. Each entry can represent individual requests, kind of like this one. And then logically, this array looks like a ring buffer. So every time you add a request into a ring buffer, you advance the tail pointer by 1, right? Until you maybe wrap around and reach the head. At this point, the queue is full, device is too slow, right? But if you have a batch of 32 requests, you push them into the queue, and then you write this entry, which is called the doorbell register, letting the hardware know that something has changed. You added new requests to the queue. So you, for example, can keep a tail pointer here in this configuration space. So some, like you added a bunch of them, you incremented the tail, and then you write into the ring doorbell register. At this point, it flies into the hardware, right? Hardware itself, this is kind of interesting. From this configuration space, it knows where this array of requests is located. It first, through the DMA, reads the tail pointer. It's one DMA transaction. Then it says, okay, I know that I have like 3 new requests. And requests might not contain data because it's just the ring buffer, right? So the queue itself doesn't have actual data which flows to the device, right? But it will contain pointers to some user buffers somewhere in memory, right? And they can be anywhere in memory. Agree? And then the hardware just fetches them either with a single or with multiple transactions. First fetches the entries from the queue back to the device, then it follows the pointers, and then it issues another DMA transaction to read all of it, right? But the beauty of it is the CPU is not involved because the CPU rolled the, what is it called, doorbell register, and after that you're done. You can run some other application. You can do a context switch, play music or whatever you want, right? But all of it is handled by the device. And so this one is burning its own CPU, which sits over here, like follows those, chases those pointers, does the DMA of if it's a write request, like in this direction. If it's a read request, it will just, this request will specify the address which the user requests for reading, and then it like fill in this sync with data, right? What happened? Now it's fully asynchronous. In fact, while the device is processing some of those requests, maybe this guy returns back to the user and user issue another read, right? And so on. And like we have a bunch of requests in flight, and then we like essentially like dividing this 20 per thousand, we are dividing not by 32, but by some other number. Maybe it's limited by the size of those queues, but by a large number, right? And in fact, but you got the main idea, right? In fact, it goes kind of further away or further into this game. They say, look, by the way, we have different kinds of queues. There is like, they do this separation of, it's called control and data planes. So one queue implements, or a set of queues implements control operations, like I'm configuring the device and everything. And a bunch of queues implement data operations. And those queues are actually mapped to different cores, which means that submission of this read requests can happen on multiple CPU cores. It's not just a single read. It actually happens on multiple cores, and device actually can support, I forgot the exact number, but it says up to, wow. I forgot exactly how, in the specification, I don't remember exactly how many, what's the max number of queues and stuff like that, but really you can like have a couple of queues per core, and which means that there will be no locking or no synchronization between these queues. It will all go through the PCI from different cores, right? And another beautiful idea, which I kind of didn't discuss, is that instead of sending a single interrupt, it actually can, the modern hardware allows you to generate interrupts, and it's called message signaling interrupts, and route them to specific cores. So instead of saying all interrupts are suddenly going to one core, they are like evenly distributed between the cores, which means that, you know, the interrupt load, if you want it, will be actually like evenly distributed between the cores as well, right? Okay, so I probably just ran out of memory a little bit, so let me stop here. But that's essentially, that's the beauty of those interfaces. And I will come back, maybe spend a little bit of time on NVMe, but if you think about it, network interfaces is going to have a similar idea. The layout of those queues can be a little bit different. So instead of multiple submission and completion queues, sometimes it's a single queue, and there will be a bit here saying that the request is completed, but it's just the details. The main idea is this, but this is how essentially those fast interfaces work. Okay, let me stop here, and then I will probably come back a little bit to this topic, but we're almost there. Okay, so for now, okay, that's it. Thank you. And I will try to assign the homeworks soon. Maybe actually